Hello everyone. In this video, we will learn graph traversal techniques. Hope you would have seen my previous videos of graph introduction, graph part 1. So we all know that graphs are a powerful and a versatile data structure that easily allows you to represent a real-time relationship between different types of data. Graphs are a common method to visually illustrate the relationships in the data. The purpose of graph is to present the data that is too complicated to be described adequately in a text and in a less space. So in this video, we are going to cover introduction to graph traversal techniques, followed by graph traversal techniques, breadth first search and depth first search, which is very widely used. So when I say that it's traversing a graph means that we systematically visit and process each node in the graph exactly once. There are two graph traversal techniques described. The first one is depth first search, second is breadth first search. We also refer it as DFS and BFS. This technique is applicable to both directed and undirected graphs. The BFS and DFS traversal of graph for a particular graph G, it won't be unique because a traversal depends on both the starting vertex and order of traversing a node, as well as how many adjacent vertices are there for each node. So if you take a same graph, if you find a DFS or a PFS traversal for a graph taking different source vertex, of course the traversal would differ. Over here in an example, we are going to assume that the first node is a source node, whether our nodes are numbered using 0 to n or they are numbered using an alphabets. So the first alphabet A or the first number in a graph would be our source vertex. Let me go for a breadth first search. So in this method, after visiting a vertex V, that is a source vertex, we must visit all its adjacent vertices which are directly connected to that before going downwards to a next level to visit that particular vertex. So in this technique of traversal, it would be making queue to keep track of next node to visit. It also keeps track of all the nodes that are not visited till now. So in this example, you can see we have taken S as a source vertex. We have three adjacent nodes to S, A, B and C. So unless and until we are done with ABC, we will not go for a next level. So we can see A gets visited, followed by which B would be visited, followed by which C would be visited. Once this is done, we will have to check for adjacent vertices to A. So we can see over here D is an adjacent vertex to A but has not been visited yet. So D would be the last vertex that would be visited. This red arrow just shows the path in which it gets visited. Let us go for one more example using Q. So this is a bit bigger graph with 9 nodes. Here we are assuming that A is our source node. So we have marked it as a visited over here. This is the array that keeps track of a list of visited vertices in an order. This is a queue. Front is over here. Rear is this end. So as and when the entry comes, it would be over here from a rear end and it would be removed from the front end. So let us go for an example. A is our source vertex. We have three different vertices B, D and E that are adjacent to A. So once we get these three vertices, we will have to enqueue it in a queue. So B, D and E is enqueued. Once this is done, all the adjacent vertices are marked. We will remove the first vertex and we will process the same thing. B has been dequeued from the queue. We can see over here. Now next step would be storing an adjacent vertices to B inside our queue. So B has an adjacent vertex A that has already been visited, E that is already in a queue, and we will then go for C. So actually we'll have to store C and E both inside a queue. So C and E has already been inside the queue. Now next vertex that comes out, always vertices are removed from front. So D is coming out, storing over here in an order of traversal. Let us mark the vertices of D, adjacent vertices of D inside a queue. So G is an vertex which is adjacent to D. A has already been visited, so we will not enqueue it again. So G is enqueued. You can see over here. Once this is done, we are done with our task. We will and dequeue one more vertex, which is E, and we'll store it over here in a traversal. Once E is stored over here in a traversal, we will have to check for adjacent vertices to E. E has an adjacent vertex B, which is already visited, A that has also been visited, and the other one is G. So G is required to be enqueued in a queue. Although it is present, we have to enqueue it again because we don't know whether it is present or not. Every time we won't be checking for the values present in the queue. Next comes out is C. Let us go for the same. B has already been visited and F is required to be enqueued over here. So F would be enqueued. Next vertex comes out is G. The adjacent vertices to G are D, E and H. D and E has already been visited, so we will enqueue only one vertex, which is H. Now we can see the time to dequeue another G, but G has already been visited. So next vertex is G, but that has already been visited. So we will just dequeue this, we will just remove this from the queue. We will not add it over here in order of traversal because that has already been marked as visited. So we'll just dequeue this. Next one would be F. F comes out. We will check for all the adjacent vertices to F. F has only one adjacent vertex, that is C, but C has already been visited, so we will not add anything to an existing queue. Next thing that comes out is H. So H would be marked over here. H is the current vertex that has been visited, and adjacent vertices to H are G and I, but G has already been visited, so we will just add I to a queue. I has been enqueued. Now the next value to dequeue is I itself, so I comes out, and I has only one node that is adjacent to I, which is H, and has already been visited. So this is a BFS order of traversal if we take A as a source vertex. Let us go for how we are going to implement this in C language. So first thing we would need is a queue. I hope you would have seen my videos for queue implementation. The same implementation is required to be written over here. So in this video, we are just going to write a function for BFS traversal, assuming that you all know how is queue created and how this enqueue and dequeue function works. So here I have taken queue of size 10 followed by which front and rear, which is initialized with -1. G is a graph that stores my vertices and edges connections. Visited is a list or an array of a visited node, the order of traversal that we have maintained in an example. E is empty, E is full, and Q and TQ would remain same as an array implementation of Q. Let us now have a look at C code for BFS traversal. So in this, what I did is I did few initializations. I marked count to be equal to 1 because a source node is always visited. And I have visited my first node, visited of 0 to be equal to 1. Going for next, every time a node gets visited, I will mark its index to be equal to 1. So suppose if I visit my fifth node, so in that case, visited of 5 will be stored as 1. It will be marked as 1. So starting with zeroth vertex has already been visited, so it is marked as 1. So this is just printing purpose. Followed this for loop, j equal to 0 to j less than n j plus plus will iterate over a particular row I, which is my current vertex, whose adjacent nodes are required to be checked. For each of these columns, I will check for if it has a connection with I? If yes, it means that it will have a value 1. So g of ij not equal to 0 is to check for, is there edge between I and j? If yes, then we will check for the second condition. That is, if j has already been visited, if that node has already been visited, then that would have been marked with 1. In that case, if visited of j not equal to 1, if it's not visited, then and then I have to enqueue it, otherwise I don't have to enqueue that particular node. This loop iterates for n number of times for all the columns for checking the connections and checking for a visited node. Now once this is done, next step would be dequeue the first element in a queue. So that's what we are doing. That would be my next I. Now I'll have to check for if I has not been visited. In that case, I'll have to visit it. I'll have to mark it, the visited array for that particular index as 1. The case that we had G for 2 times in a queue, but that G was already visited in a previous pass. So in that case, this condition becomes false and we will not mark that one again and we will not increment the count. Again, we will not print that G has been visited. So for that purpose, we need to keep this condition. Once this condition goes true, a node, ith node would be marked as visited, count would be incremented by 1. This do while loop continues unless and until there is an empty queue or count not equal to n. Why we need to keep this condition is, it may be possible that there are some isolated nodes in the graph. Isolated nodes are those nodes which are not connected to any other nodes. Suppose that in an array of 10, we would have marked the whole row as 0. That shows that that particular row is not connected to any other nodes in the graph. So if your queue is empty, you don't have any more nodes to process, this loop should not go into an infinite loop. So for that purpose, this condition is kept, followed by which we are writing that count not equal to n. It may be possible that there are few values in a queue which has already been visited, but we have reached to our count. That is, we have visited all the nodes. In that case, all the values in the queue are of no use. So in order to save that time, we are writing this particular condition. Let us go for DFS traversal. In DFS, that is depth first search, we start at a vertex V, first visits V, then some neighbor W of V, then some neighbor of W that has not been visited before, and so on. When it gets stuck, the DFS backtracks until it finds the first vertex and still has a neighbor that has not been visited before. It continues with this neighbor until it has to backtrack again. Eventually, it will visit all the vertices reachable from V. This technique uses stack to keep track of a next node to visit. DFS makes use of stack to store the adjacent vertices. So here in an example, I took S as a source vertex. So this will work like S, from S we will go to A. A has an adjacent vertex D, so it will process that first. D has an adjacent vertex C, so it will process C and B both, but B comes first, so B will be visited first. B has an adjacent vertex S, but S has already been visited, so it will backtrack to D. Once it comes to D, it gets that yes, one more vertex is left to be visited, which is C. So C gets visited. Then again, when it starts from C, so C to S, but S has already been visited, and we have reached to N. All the nodes are now visited. So this is a DFS traversal. Let us go for one more example using stack. Again, taking the same example that we took it for BFS with a 9 nodes and marking A as a starting vertex. Now here we are going to maintain a stack in order to store the vertices. There we have enqueued an element in the sequence, in the alphabetical order, but over here we are going to take it in a reverse order because last in first out. We won't say if I take an adjacent nodes to A. So in that case, B, D and E. If I push it in the sequence B, D and E would come out first. But I don't want that. What I want is it should be in an alphabetical order. So B should be on the top. So we will push it in a reverse order. E, D and then B. So that's what we are doing. E is pushed, D is pushed, followed by B. Now once this all the nodes are pushed onto a stack, next thing to do is to pop the last element out. So B would be popped out and stored in an order of traversal. Check for the adjacent vertices of B and push it onto a stack. Adjacent vertices we have A that has already been visited, then is E and C. You can see E is pushed onto a stack, C is pushed onto a stack. Now once this is done, we will go for again popping the next element out. C has been popped out and adjacent vertex to C, which is F, has been pushed onto a stack. Next one would be popping out a next element F. F has no adjacent vertices to be pushed. It has only one, that is C, that has already been visited. So nothing would be pushed onto a stack. Next element to pop out is E. E is popped out. Adjacent vertices to E, that is B and A, has already been visited. So only G would be pushed onto a stack. Next vertex to come out is G. G has an adjacent vertex D, E and H, out of which E has already been visited. So it will push H followed by D. Next vertex to come out is D. D has an adjacent vertex A and G, which has already been visited. So nothing would be pushed onto a stack. Next one is H comes out. H has an adjacent vertex G and I, out of which G has already been visited. So I would be pushed onto a stack. Next vertex to come out is I. I has a vertex H which is adjacent but has already been visited. So nothing would be pushed onto a stack. Now we reached to a count N. But still we have some vertices lying on the stack. But just because we have visited all the vertices, these two vertex are of no use. So we will just pop it out without processing it. And this shows the traversal, that is an TFS traversal of this particular graph when we are starting with the vertex A. D and E are the vertices on the stack that has also been visited previously. So we will just pop it out. And this is an order of traversal. Now for this also we need to go for an initial setup. Hope you would have seen the video of an array implementation of stack. So that has a stack followed by top, and this four functions designed already: is empty, is full, push and pop. So it's assumed that you will check it out, and here we will just go for a DFS traversal function. These are two additional things that we are taking: declaring at a global level, graph which is required to be stored, and visited node that marks the node to be visited. In this code, this is very similar to the one that we have seen for a BFS traversal. The difference is there we took a for loop in an incrementation order. Here we are going to take it in a decrementation order because stack is last in first out. So every time we have to push it in a reverse order. So this is the difference, followed by which the difference is push and pop. There we used NQ and DQ. The other thing remains same. There is no change in the condition. There is no change in any other part of the code. So here also we are taking visited of 0 to be equal to 1 because first node is always marked as visited, which is our source node. Followed by which we are taking a do while loop that will continue till stack is empty or count reaches n. Here we are taking a decrementation loop just because we have to push the nodes in a reverse order. The way we pushed it, E, then D, then B. For that purpose, we have to take this for loop in and reverse order. This is the condition, the same condition to check for is there any edge between I and J, and the second condition to check if that node has already been visited. If visited, we don't need to visit it again. We don't need to push it onto a stack. Once this loop is done, we will come out and we will go for popping the next element out. We will check for if that has already been visited. We will not print it. We will not increment our count. Rather, we would go for next iteration of do while loop. But if it has not been visited, we will mark it as visited using visited of I equal to 1 and we will increment our count. So this is a C code for DFS traversal. Thank you everyone. Please like and subscribe my channel for more videos.